So I'm Vazquez,
I'm Eduardo Quintana,
and we are BAM.
Blind Assistance Map.
So we're going to first discuss our problem, presentation, and verification.
So our problem statement, being blind is a problem that's faced by people in their everyday lives, and what we want to do is be able to help them adapt to their new lifestyle. So what Lewis and I are trying to do is make an affordable and innovative way to help the blind. So according to the World Health Organization, in 2014, 15% of the world's population was blind, and with that 50%, 29% was below the poverty level, so they can't afford all the expensive software that can help them.
And then now we're going to analyze prior solution attempts. The first one we're going to talk about is called the Low-Vis Guide. This is an application that you can download on your phone. Some pros of this application is that it's very accessible. Now that most people have phones and tablets with them. Some cons are that this does have to be programmed by the person who is running the event, and so this map here is designed more for events where there's going to be a large number of people, and you would program the layout of the building that you're going to be in, and then the blind person would listen to the phone speak to them about how to travel through the building.
So the second product we have is the Orcam My Eye. And so the Orcam is My Eye is a wearable device almost like glasses, so you put them on and it helps you recognize whose face is who. And so it helps, it's a slick and simple design. It's like any other pair of glasses, you put them anywhere. And so some problems about it is that it has to be programmed for faces. You can't just put them on and recognize who's who. It has to be programmed to know like whose face is who, and it's sold at $3,500. And our third product is the Mini Guide. So the Mini Guide is a small product that uses ultrasonic echolocation, so meaning that it uses vibration to detect objects that are by you. So if you were using it and say a chair was in front of you, it would vibrate, but that's the only thing it does. Other than that, it's listed at $545.
And so here are some design concepts and ideas. The first design concept or idea that we got was from the MIT Inform, and this is a table that is rises and lowers to different textures, and here you can see there's a person on the other side of this screen who's actually putting their hands into a camera and able to control this ball here, and so this is the setup that they have for those pins to actually rise up or lower, and this was not designed for the blind, but we'd like to incorporate this in a map that can actually make a textured surface for the blind to follow.
So once we saw the MIT Inform, we immediately thought of the pin art. So the pin art is designed to be a toy for kids. It's inexpensive, so meaning it's like less than $20. Like we found one for $12. So another good thing about it is it's easy to dismantle. So we took it apart and see what it can do.
And then sonar scanning was the next concept that we considered. This here is done in processing, and it's an image of what this sonar here is picking up in a room. And so the red here would be an item in the way. This is using a sonar, a simple sonar called HC SR04. And then deciding that we're going to use our Arduino Mega controller. This is like the larger version of the Arduino Uno. And the reason why we decided to use this one is because it has about 54 digital output and input pins and 16 analog pins. It also has a higher processor than the Arduino Uno. And so our STEM applications. The first STEM application that we were using is programming. We used processing and Arduino. Processing was only used for us to use like a visual representation of what the sonar was actually reading. And Arduino is the interface that we're using to control the pins using that Arduino Mega board.
So we also use computer-aided design, which we use Autodesk Inventor, and what we did was that it helped us visualize everything that we were going to make before actually making it. So it helped us like see where the components were going to be, what was going to fit in where. So it just helped us along the way.
And then doing our sonar calculations was another STEM application. Knowing that speed is equal to distance over time, and knowing that the sonar is sending out waves that travel to the speed of sound, we can resolve for distance and then calculate that distance, knowing that the speed of sound is 343 meters per second. And so design viability, will this actually work? We had to upgrade our sonar from the, like I said, the standard HC-SR04 sonar to our LV Max Sonar EZ0. The biggest difference between the two sonars is the range. Our new sonar reaches up to 16 feet in distance, in a radius, and our old sonar was only 18 inches, so that's a really big jump. The only downfall about this upgrade is that it did take 50% of our budget.
So our first prototype with the pin art, we wanted to divide each section into 15 sections for each part of the pin art. So we wanted to put a servo motor under each of the section that we divide, and we'd want to put it up. So a servo would be responsible for one of the sections rising up for the pin art. And we also tried to do something with the magnet, since the pins are magnetic, but we ruled that out.
And so our initial prototype here, this is the bottom where we glued all the pins together. And at this point, we were not able to use the 1,862 pins that the pin art has. We were actually sectioning it out. And so we realized that this was getting really heavy because of the glue and all the metal pins. And it wasn't really what we wanted anymore. The idea about using the pin art was that we would be able to move each individual pin. And because we were doing sections, we had to consider a new design. And so this is an animation done in Inventor of our new design. And so I'd actually like to show that again, because this is a really big important reason why we like to use Inventor to analyze our models and before building the actual prototype. Here you can see that the intersection where the servo motor is turning is actually hitting the enclosure of the pins. And so this was a simple fix. We just had to have the motor spin the opposite way. But in other cases, it could be something more like measurements or changing the size. And so the way that we modeled our enclosure was actually to fit all the 16 servo motors on the inside. And that was all done in Inventor before we had to build any prototypes.
So our changes in design, the old one was the pin art. Like I said before, we want to do the 15 sections. So the pin art was 5 inches by 7 inches, and the metal pins, and it was plastic enclosure. For our new design that we wanted to make in Inventor and 3D print was 16 sections, and it was 4 inches by 5 inches. And instead of the enclosure for the plastic, we wanted to use the 3D printed material for the enclosure over here for the pins.
And so we're constructing of a testable prototype, bringing our new design to life. The 3D printing process. The 3D printer that we were using was the MakerBot Replicator 2X. And all these here are actually failed prints or prints that did not work out. And the biggest difficulty throughout the process was actually getting one solid enclosure to be printed. This took about 2 months, and we went over 12 failed prototypes.
So our assembly process. So what I'm doing in that picture is getting one of the 3D printed items that we did, and I'm giving an acetone rub, which is pretty much a nail polish remover, which makes the 3D material more smoother, much slicker, making it look nicer to get rid of the rubbish material.
And then for each one of the servo motors that we had to solder 3 wires or extensions to the wire. And so here is how we were soldering the extensions to those wires. It was about 50 wires that we had to solder. And so that's why you can see this big mess of wires here. Those are all the different wires that had to be connected from the servo to the Arduino and to the 5 volts and the ground. And then here is another image of having to assemble those pins within the enclosure. It was actually more difficult than we thought it would. It took us about an hour to actually get the first time for all those pins to go into the right section that they were supposed to be. And so this is an image of our final prototype. And so here we can see up front is that our upgraded sonar, and then in the back we have our port for our 9-volt battery. Now testing and planning our prototype.
So our data collection, so the final prototype we tested 16 sections. Like I said before, it was going to be a total of 16. So the front servo, it rotated from 15 degrees to 165 degrees. And the 150-degree angle was going to be divided into 4 parts, A, B, C, and D. And so the rows were also divided into 4 sections. And like I said before, it was A, B, C, D, and those sections were going to be 1, 2, 3, 4.
Yeah, so each vertical section accounts for 3 feet of distance, and so the max distance that we were going to give our sonar was going to be 12 feet. This was actually, well, we'll talk about the data. And so in our data analysis, reaching the 12 feet is this Sec 4 section here, and that's where we got the least amount of accuracy. These percentages in here describe the times out of 10 that an object was detected in that specific section. And so, like I said, when we were reaching the 12, we're looking at 60 to 70%, which is not what we expected. We expected it to reach all the way up to 16 feet. But we believe that the reason why the sonar was not as accurate at those 12 feet was because of the movement of the servo that the sonar was on. And things like temperature and the conditions of the room can affect the speed at which sound travels. And so those calculations might be a little bit less accurate the further you are away from the sonar. But for the most part, within the first 9 feet of the map, the accuracy was from 100 to 80%. And then external evaluation and professional advice. So we teamed up with Luke from the Chicago Lighthouse, and he is manager of technology for assisting the blind. And the Chicago Lighthouse is an organization that's actually world known for helping veterans and people with disabilities. And so Luke told us that he thought that our idea was well thought and very helpful. Unfortunately, he has not been able to see our final prototype, but we have contacted him and he is interested in seeing it. And then our final evaluation, moving forward, and acknowledgement.
So the overview of our project was a fun experience. You know, we made mistakes but along the way, but from those mistakes we learned a couple new things. And our budget for this whole project was $50, and I think we did pretty good other than the sonar.
We exceeded the budget a little bit. I don't think we went over more than $12, and that was because we were buying extra things and there was some changes to what we had originally planned. But yeah, overall the hardest part of the project was the 3D printing process. Our 3D printers aren't as accurate as we would want them to be, and so it took us longer to get an actual final prototype built. But overall the experience was rewarding. And so our acknowledgements, we'd like to take the time to thank Mr. Roach for his support and encouragement throughout this project. He's always been here and dedicated time to us during breaks, after school, before school. He works with our schedules to make sure that we have time to work on this. And without a doubt, this project would not be possible without his support. We'd also like to thank Luke Scriven from the Chicago Lighthouse, because he was also very helpful and gave us knowledge about technology with the blind and where he sees technology going into the future, helping the disabled. And lastly, we'd like to thank our administration for allowing the time for us to present and giving us the resources that we need. Thank you for your time.